Hello, welcome to the Atom Render Pipeline Interface session. My name is Tao Qing, and I am a Senior Graphics Engineer at AWS. This presentation is mainly focusing on giving you a high-level overview about the Atom Render Pipeline Interface. I will go over the design goals, architecture, the subsystems, features, and tools of the RPI. In the end, I will talk about using RPI for graphics feature development. If you are interested in Atom Renderer, or you want to develop a graphics feature or create a non-game application with Atom Renderer, this session will give you some information you may need. Here is a list of design goals for Atom Renderer. First, we wanted to support a fully data-driven rendering pipeline. This gives developers the ability to create and customize a render pipeline which is the best fit for their applications, and they don't need to change the renderer. Second, the renderer needs to support modular graphics features. These graphics features are independent and they can be enabled or disabled by choice. The renderer should also have good support for multi-threading, especially for the simulation and the render data submission. The renderer is not just for certain particular type of games or applications. It can be used for many other fields or industries. The renderer is extendable. Adding a new platform or a new hardware feature should be trivial and won't affect existing work. RPI is an important part of Atom Renderer. Its design is directly contributing to achieve most of these goals. I have highlighted the goals RPI is focusing on, except the last one, which is mainly relying on the render hardware interface. Next, let's take a look at the architecture of Atom and the RPI. This diagram shows the overall architecture of Atom Renderer. Let's go over it from bottom to top. The render hardware interface defines a layer of APIs which has several different backend implementations. Currently, we already have DX12 for PC, Metal for Mac OS and iOS, Vulkan for PC and Android. The render pipeline interface is built on top of RPI. We also have some asset builders which build basic assets for RPI to use at the runtime. The graphics features are built on top of RPI. For each of this module here, we call it our feature processor. Each of the feature processor is independent and it manages its own graphics objects, customized passes, simulation, and the render data submission. Developer can develop a new feature processor and provide it as a gem. This component on the top layer is how we expose the features to O3DE engine to provide the interaction between game objects and the rendering objects. From the last slide of Atom architecture, it's pretty clear about some facts listed here about RPI. RPI is a platform-independent API. It implements on top of RPI. It's the main interface for developed graphics features. People may use RPI directly, but they may find they need to do a lot of handcrafting work to set up the rendering frame. Other than those facts, one important rule RPI has is to bring data to the rendering frame as well as using this data to construct the rendering frame. And because of that, RPI defines fundamental graphics resources such as buffer asset. And because of that, RPI defines fundamental graphics resource assets such as buffer assets, image asset, shader asset, material asset, and so on. It also defines data presentation of rendering pipeline and uses it to construct the rendering frame. Here is something more about RPI. RPI manages and renders multiple rendering scenes and rendering pipelines. I will talk about it more in the next session. It sets up the architecture to collect, filter, and dispatch rendering data. It defines the interface for future processors. This is the main way to connect a graphics feature with the RPI system. It parallels a graphics feature simulation and rendering. There are a few things to clarify what RPI doesn't do. It doesn't include any of the high-level assets, such as the animation asset, terrain asset, etc. It doesn't provide any specific rendering pipeline. The forward plus red pipeline is defined in Atom Common Feature Gem. It doesn't include any implementation for particular graphics features. Let's take a look on RPI's execution. This diagram shows how our frame is executed with RPI system. Both the simulation and the prepare render of each feature processor are executed in parallel, and they are also decoupled. In future processor simulation, you could expect to see work done here, such as CPU particle update, scheme mesh animation, or something more common such as a shader resource group update. In future processors prepare render, they submit job packets to views, or submit job items to passes they know of. The RPI frame starts when all the preparation is done, and during this frame execution process in RPI, it will call render passes or callback functions. In this session, I will talk about the major systems and features. RPI supports multiple rendering scenes. For each scene, it may contain a set of meshes, lighting, skybox, and so on. Any rendering content in one scene won't be affected by the other things. Each scene can be configured to have its own selection of feature processes. In current O3D editor, we have used different scenes for 3D level viewport, the material asset preview, and the LY Shine UI editor viewport. The Atom example viewer has a simple example to show how to create two scenes with RPI. A render pipeline in RPI describes how to render a scene, and it can be forward plus, forward, deferred, etc. A render pipeline is usually created through data files. In RPI, one scene can have multiple render pipelines. Each render pipeline can be created from different render pipeline templates. This means we can render the same content to two or more different rendering pipelines at the same time. When future processor submits draw packets for rendering, it doesn't need to know how many render pipelines are active and what they are, as long as the material matches the render pipelines. This is a screenshot of O3DE engine editor. I'm going to show you how it uses two things and three render pipelines. There are two viewports for a 3D level view window. The viewport on the left is the first render pipeline of the scene for the level. The viewport on the right is the second render pipeline of the scene for the level. On the bottom left side of the editor, it's the material preview. It's rendered with the scene created just for the preview. Path system is the core system for data-driven render pipeline. It maintains a tree structure. The nodes of this tree are all passes. The leaf nodes are render passes, which are a response to submitting draw items or dispatch items. This tree structure can be constructed from some path files. The path file is a JSON file. It contains input and output of a path and the connections between passes. Each render pipeline has a path tree, and its root is the direct child of the path system tree root. My coworkers had a workshop called Atom Deep Dive, which gave you more detailed information on how to work with path system. Here I want to show you some examples. In Atom Sample Viewer application, it switches between two render pipelines for different samples. The screenshot on the left side is a render pipeline used by all the iTry samples. This render pipeline only has 3 passes. This is because we want a minimum complexity with the render pipeline, so the iTry samples can focus on validate certain low-level APIs for each backend. It still has 3 passes because we need one for ongoing menu and one for copy swap chain. The screenshot on the right side is the render pipeline used by most of RPI samples and future samples. This render pipeline uses the forward plus render pipeline provided by Atom Common Future Gem. It enables all the available graphics features from that gem too. This render pipeline switch is happened at runtime, and it's around 100 lines of code for the switching. The shader and material system is fully data-driven. It handles shader and the materials loading, creation, updating, and hot reloading. There are some important concepts you would want to learn first if you want to create customized shaders and the materials. First is the shader resource group and shader resource group semantics. Also the AZSL shader language. The AZSL is similar to HLSL, but it does have some unique syntax to work with Atom Renderer. Before creating a customized material, you will need to understand the relationships between shader, AZSL, material, material type, and material functor. My coworkers had a Working with Atom workshop, which I believe they had shown some tutorial on how to work shader and the materials. RPI has defined some basic assets, which the data they contain are usually required for rendering. We have set up such a pattern to create these objects from data. First, use the creator class for create the assets, which encapsulates all the data needed, then creates the runtime object from the asset. The asset creation process is usually happen as asset processing time by asset builder. For example, the image processing item gem has a builder to convert image files to .stream image asset file in cache. If you want to load some third-party data file directly at runtime, you can utilize the creators to create these assets at runtime. Image and buffer are both GPU resources. RPI has two subsystems for each of them to provide object management and default pools for allocation. The image system provides image instance database, image streaming control, texture hot reloading support, and default image pools. The buffer system is similar but simpler. It also provides a helper function to create a buffer. So we have talked about these RPI assets. Let's take a look on how they are used to make a draw item. When you needed to draw something, you needed to submit a draw item to iTry command list. A draw item usually contains the input streams and the shader resources, but they are not mandatory for some use cases. The pipeline state is required for a draw item. To construct a pipeline state, it needs some information which includes shader functions, input layout, output layout, and the render states. The buffer data, which usually come from model, provides data for input streams. The material provides data for shader resources. It also provides render states for pipeline state. The input layout is a little bit complex. The data comes from combining the input contract information from shader and the stream information from model. The output layout information is from past output attachments. The diagram here is showing a common case. Some of the data can be configured through other ways. For example, the dynamic draw system doesn't need a material for its render states or shader resource data. The dynamic draw system provides a convenient way to submit dynamic draw data from CPU buffer every frame. It utilizes a ring buffer to copy index and the vertex buffers to GPU buffers with minimum cost. It also provides a helper class called dynamic draw context to prepare the draw context for you. We are using it for O3DE UR system, the debug font, and the ImGUI rendering. RPI has a CPU calling system which does view frustum calling and the CPU allocation calling. The allocation calling is for PC only. The calling system is thread safe, which means users can register or update their callables from any thread. The calling jobs are executed in multiple job threads. Using the calling system is simple. You just need to create the callable for your object and register it to the calling scene. If the object's calling data is changed, you need to tell the calling system to update the callable. The colon system will submit the callables draw data once it's not called. You shouldn't need to submit the object's draw data to the viewer yourself. Item provides some tools which could help debug your renderer. Most of the tools are backed up by RPI. Today I will go over these tools. The pass tree tool shows all the passes in the pass system and all the attachment of each pass. It can preview image attachment at any time point on the screen. It can also read back the image or buffer attachment data from GPU. This functionality is implemented by RPI's attachment readback class and attachment preview class. Developers can also use Python or Lua script to do the capture. For example, the script of color grading workflow is using the capture function to capture image output before display mapping pass. When you select the attachment, you can see the history of this attachment in the frame and which passes use the attachment. The attachment preview is located over the left bottom of the viewport. The GPU profiler has 3 tools. The timestamp view shows GPU execution time for each pass. The pipeline statistics view shows some draw statistics such as a vertex count, primitive count for each pass. Both of these 2 tools are using RPI GPU query system to add queries to each render passes to collect the data from GPU. The GPU memory profiler is showing the estimate GPU memory allocation data collected in render hardware interface library. These tools can give you a quick overview on GPU usage to find if there are some passes are too expensive or any unreasonable GPU memory usage. Atom has a runtime CPU profiler tool which allows us to collecting CPU profiling data and visualize it. The visualization shows timeline per thread. This CPU profiler has been moved to AZ core, so any gems can add profile markers and utilize the tool to do profiling. The Transient attachment pool tool is showing transient attachments allocation data collected from iTry. Transient attachments are the attachments which lifetime span are inside a frame. We use heap aliasing to create the transient attachments. It could be helpful if developers are interested in optimizing the render pipeline peak GPU memory usage. In this capture, there are 3 heaps used for transient attachments. The horizontal direction is the timeline. The width of the rectangle is the lifespan of this attachment. If you cast a vertical line, all the rectangles it crosses are the attachments alive at that time. In this picture, you can see the peak is determined where I put the orange highlight. Next, I will talk about using RPI for develop graphics features. When create a new graphics feature, the first thing you may need to add is a feature processor. A feature processor manages the rendering instance in its owner thing for this feature It also has the entries which enable parallel simulation and run data submission with other features. There are exceptions which you may not need a feature processor. For example, IMGUI rendering. And since IMGUI already has IMGUI context which manages the render data, the IMGUI render path is enough to handle the rendering. We also have an example which we group several post effects together and use one feature processor to handle all of them. Next, does the graphics feature need new passes? Because some draw data can be submitted to existing passes. For example, the particle effects can be submitted to existing opaque forward pass and the transparent pass. If you find that you need your own passes, you can encapsulate the new passes under one parent pass for easy management. It's possible you need to acquire data from other features. For GPU data, such as constant buffers or render targets, you can read them from shader resource group or from scene or view. For data in CPU memory, you can use eBus to request the data. There are a few important notes for the implementation. Communicate between past and the future processor should happen in the same thing. The job packets should be cached until the frame is end. The future processor needs to be thread safe with certain functions, especially the simulation, the render data submission, and the render instance manager functions. The future processor may be responsive to batching and instancing. Thanks again for joining this session. If you have any questions, you may jump on this Discord channel and post your question there. You can start a discussion in GitHub, which we will check at the triage meeting.